Hey there, welcome to another video. So in this video, we are going to start something new. We're going to start talking about sequences and series. Sequences in this video, series in the next video, and then we'll talk about some specific types of sequences and series like the arithmetic and the geometric sequences and series, discover what they're all about, and then have a mathematical proof by induction. And that's the next several videos. So kind of a different unit for us before we move on to anything else. So when we start talking about sequences and series, I need you to understand what they are, how they're created, and what we can do with them. So when we talk about sequence and series, there's a difference between them. Sometimes students get confused. A sequence is simply a list of numbers. They're not added, they're not multiplied, they're just listed with commas between them, and they're from some sort of a formula, some sort of a sequence expression that's based on the index of your term. And we'll talk about that as we go. What a series does, a series takes that sequence and adds it up. That's the difference between a sequence and a series. So a series has a lot more math involved in it. There's a lot of formulas that we can do to add up series, but sequences, we don't have that because you're not adding them. You're just listing it out. So a sequence is simply a list of numbers that's given by some sort of a formula, really. So that's what this really says. A sequence is a list of numbers given by a formula determined by the index of a term. What in the world does that mean? Well, an index is the number of the term that you have in your sequence. So we should be able to say, oh, can we find the second term, the first term, the fifth term, the 100th term, given by whatever our formula is for that particular sequence? The answer is yeah, we should be able to do that. So when we start talking about sequences in the formula, you're going to notice that you have this little subscript. We call that an index. And given an index, you should be able to plug that in. Look how it's related. There's an a sub n, and then inside of your formula, you have another n. This says to find a term of your sequence, you're just plugging in whatever term you want to find. So do we want to find the first term? Plug in 1. Oh, that would be a sub 1. That would be the first term. Plug in 1. It would tell you what the value of that term is. And we can find as many terms as we want to. We can find whatever term we want to simply by plugging in the index of whatever term we need to find. This is the standard way that you see sequences. Sometimes you'll see them in brackets. It's also very, very common. Generally, we write our sequence in brackets like that. So let's go ahead and jump right into it. A sequence is a list of numbers given by a formula, and if you want to find any term, you just plug in the subscript or the index of whatever term you want to find. So we're going to find the first 5 terms. We'll talk about a little bit more after that, but we're going to go ahead and practice right now. So let's say we wanted to find the first term, a sub 1. A couple of questions you might have is, well, what can n be? Can n be decimals? Can n be 0? Can n be negative? Well, n can be 0, like the 0th term. Again, awkward to say that, but you can have that. N cannot be fractions, can't be decimals, can't be negative. We call them natural numbers. So a sub a natural number. The index is always a natural number, 1, 2, 3, these counting numbers that we have. So you're not going to be plugging in like 3/4. Thank goodness, right? We're just plugging in whole positive natural numbers to get these terms. So if we want to find the first term, we're going to take 1, our index, we're going to plug it in. So a sub 1, notice how the 1 replaces the n here and must replace the n here, just like a normal function would. So we plug in 1. So a sub 1 would be 1 squared plus 1. That would give you 2. Our first term in our sequence is 2. How about a sub 2? Well, if I want to find the second term, all of these terms are based on their index. And then the formula that we're using is basing whatever value we're getting out for that term on the index as well. So a sub 2 says replace your n with 2. Replace your n with 2. That would be 2 squared plus 1. That would give us 5. Well, how about 3? 3 would be our third term. Let's replace that with 3. For the fourth term and fifth term, we're doing exactly the same thing. So a sub 4 says take your index, replace it with 4, replace your n with 4. They'll give you the fourth term in your sequence. 17. And you might start to develop some patterns here. You see, a sequence should be really a patterned list of numbers. It should have a pattern to it. So if you look at this, we start with 2, sure. If we had started with 0, a sub 0, we would have got 1. Notice that you plug in 0, you get 1. So let's take a look at what's really happening. To get from here to here to here to here, can you see what's happening? Can you see that from 2 to 5, we're adding 3? From 5 to 10, we're adding 5. From 10 to 17, we're adding 7. We added 3, 5, 7. The next term that we get should be added 9. It's going to create something with a pattern. Now, it's not that easy to go from a pattern and get this, but I'm going to show you in the latter part of this video how to do that. A way to structure your thinking on how to get back to a formula from some sort of a list of numbers. But in general, it should create some sort of a patterned list for you. Let's check it. This should be, let's see, 17 plus 9. It should be 26, but let's go ahead and find out. So plugging in 5 would give us 5 squared plus 1, that's 26. And sure enough, this would be add 3, add 5, add 7, add 9. The next would be add 11. It's creating a list of numbers for us that's definitely a pattern. But we always have a formula to fall back on to see where we can plug our index and get the appropriate term. Could you plug in 0 if you wanted to? A sub 0. You can do that. You can't plug in negatives, you can't plug in fractions or decimals, but if you did, we would get 1. And notice, from 1 to 2, you would add 1, then add 3, then add 5, 7, 9, the next should be 11, 13, 15. We're adding odd numbers to get these. It's based on this. Now, it's kind of interesting that adding odd numbers up, starting with 1, is you can find any term by that formula. So what if you wanted to find out the 100th term? Would you really want to add up these odd numbers until you get to a sub 100? Well, probably not. You'd have to do a whole long list. Could you find the 100th term simply by plugging in 100? Yes, that's why we have a formula. So you do 100 squared plus 1. It would give you whatever term you are looking for. So we found the first 5 terms. Our list of numbers, our sequence, it has a pattern to it, is going to be, I'm going to remove the a sub 0. Two, 5, 10, 17, 26, and then it doesn't end. So the way we show it doesn't end is we put a few dots and then we close that curly bracket. So this is the first 5 terms, starting with n equals 1. And you should be told that, like, where do you start? N equals 1, n equals 0. I told you n equals 1, so we started there. You have to be told where to start. You don't have to start at n equals 1, do you? You could start at n equals 20 if you really wanted to, but you're going to be asked, find the first 5 terms of something. That implies start with 1. So if they tell you 0, great. But in general, you just start with 1 unless otherwise specified. And you'll list out the first 5 terms in that sequence. It doesn't end, and you can find any term just by plugging in whatever that index is. Hope that makes sense to you. Hope you're seeing what a sequence is. Very simple thing. Sometimes we overcomplicate it, but it's a very simple thing. Just plug in a number, you're going to get that particular term. Let's move on to the next one. So b sub n equals n over 3n. So it says to find the nth term, you're going to take whatever that value of n is, plug it into your formula, and get a value out of your term. The nth term, if we leave it in terms of n, is sometimes called the general term. So we can do things like this would go until you hit your general term, whatever your n stops at. Since our general term is given by n squared plus 1, we can do it. It looks a little funny. It might look a little funny to you. 1, 2, 3, 4. That would be listing 5 terms. In general, 2, 5, 10, 17, 26 are the first 5 terms, and you would keep doing that forever, following that pattern is what that says to you. So let's find the first 5 terms of b sub n. Let's put them in a list here. It's not really hard to do. You're going to see the pattern as we go. So b sub n equals n over 3 to the n says, I want to find the first term. Let's plug in 0. That would be 1. Oh, sorry, I misspoke. That would be plugging in 1 for the first term. So 1 over 3 to the first. If I want to find the second term, I'd plug in 2. That would be 2 over 3 to the second. And we can simplify as we go, but I do want you to notice that it's really important to be able to go backwards and get this sort of a pattern to it. What's really happening to our numerator? What's really happening to our denominator? Our numerator is getting exactly what this index is, 3. Our denominator is getting 3 to whatever power our index is. I'm prefacing something we're going to do in just a little bit. What we're going to do in just a little bit is go backwards. I'm going to give you a list of numbers. I'm going to ask you to come up with that formula for the sequence. And it's really important to be able to base whatever numbers you have on whatever index you have for your terms. That's incredibly valuable because then you can make the jump to the general term, the term based on n. That would be like the general term, the term based on n. How about the fourth? So the fourth term. So b sub 4 is how we say that. That would be 4 over 3 to the fourth. And you can see the pattern. The next term is going to be 5 over 3 to the fifth. The one after that would be 6 over 3 to the sixth, 7 over 3 to the seventh, n over 3 to the nth. That's exactly what that says to us. Now we're going to simplify these. We get 1/3, 2/9, 3/27, 4 over 81, and 5 over 243. But when we go and simplify the fraction a bit more, especially that guy right there, we're going to start losing the pattern. It's not going to be as easy to see. If you're asked for the first 5 terms, these are it. If you're asked for the general sequences, listen out, this is it. So it goes forever until you want to stop at whatever n you're asked for. Here we were asked to stop at the 5th term. So you'd have 1/3, then 2/9, then 1/9. Notice how this is getting smaller. This might look really funny to you. You go, what is happening with that? Well, this is 3/9. 1/3 is 3/9. 2/9, 1/9. 4 over 81, 5 over 247, these fractions are getting smaller and smaller and smaller. It would look like a decreasing function, almost like an exponential. Wait a minute, that is an exponential. Hopefully you find that very interesting, that is based on some sort of an exponential with a term or a base of 1/3, something over 3. So anyhow, our sequences are based on our index. We plug it in. Could you plug in 0 here? Well, sure, you would get 0 over 1. That would be 0. So you'd start with 0, 1/3, 2/9 if you were asked to start with the 0th term by plugging in 0 and finding b sub 0. We list out whatever number of terms we're asked to, and that's pretty much how we deal with these sequences. We can simplify our fractions, of course. This would be kind of nice because you can see the pattern, can't you? 3, 9, 27, 81, 243, those are powers of 3. 1, 2, 3, 4, 5, that's our index itself. When we start simplifying them, of course, we start losing that. So now listen, please listen to this. When we get to the next part of it and we're going backwards, we're going to want to make all of these terms we're given the same type of form. So we're going to say, wait a minute, that's 39981, 247. We need to make those look similar to be able to find a pattern to it. And so we'll start thinking that way. All right, let's move on to the next example. Again, find the first 5 terms. We're going to see what this part does, what that part of a sequence, that -1 to an exponent. We're going to see that all it does is alternate signs. It's going to make positive, negative, positive, negative, positive, negative. That's important for us to realize as we go back in some of these patterns, that causes us to have alternating signs. So if we see alternating signs, we're going to have -1 to some exponent. The other thing I want you to notice is that even though I've only found the first 5 terms here and then the general statement, you can find any term you want. If you wanted to find the 50th term, you'd plug in 50 over 3 to the 50th. Now think about that. 50 over 3 to the 50th. 3 to the 50th is enormous. 50 over that is going to be very close to 0. Almost like this horizontal asymptote, like all exponential that have exponential decay or decreasing exponentials get to. So this would have a horizontal asymptote somewhere. We're going to say the same thing would happen here. If I just needed to simply find a sub 10, the 10th term in our sequence, I could plug in 10. It'd be very easy to do. We're just practicing finding out what our sequence is by plugging in the first 5 terms. So let's start with a sub 1. So a sub 1 says if I want to find the first term, I'm going to let my index get evaluated here and on that side as well. So a sub 1 would equal whatever I get when I plug in 1 to n. So even though there can be a bit more work here, we're still doing the same thing. So we're taking 1 and evaluating. -1 to the 1 minus 1. So n is replaced by 1 everywhere. 1 minus 1 is 0. -1 to the 0 power is 1. And that fraction that we get is 1 over 1. So 2 times 1 is 2, minus 1 is 1. 1 divided by 1 is 1. So our first term, a sub 1, is 1. Let's do a sub 2. A sub 2 says that if you want to find the second term, let n be evaluated for 2. Now I really need you to focus on what happens with this piece as we're working down. As we do this, think about what's going to happen here. This was a 0 power. Think of it like even though 0 is not really even here, but think of it like even, and so anything at 0 power would give you a 1. This is going to be an odd exponent. Anything to a negative to an odd exponent is going to give you a -1. The next one will be even. It'll give you +1. It's going to alternate. All that -1 is doing is giving us positives for even exponents and negative for odd exponents. It's all that's happening. It's alternating our signs for us. So -1 to the 2 minus 1 is 1. That would be -1. The fraction is 2 over, 4 minus 1 is 3, 2/3. Giving us -2/3. A sub 3 is going to be similar, but we should expect that this is going to be -1 raised to an even power, giving us +1. Let's see, the third term. Take your 3, plug it in. So we would have -1 to the 3 minus 1 power. Well, 3 minus 1 is 2. And so if we have -1 to the second power, -1 to the second power, it's in parentheses, that would be +1. Our fraction is 3 over, 2 times 3, that's 6, minus 1 is 5, that's 3/5. Since we got a +1, 1 times 3/5 is 3/5. Can you see the pattern? Can you see, maybe you can see it now, you'll definitely see it on the next one. We started with 1 over 1, then we got 2 over 3, but it's negative, then we got 3 over 5, but it's positive. So there's a few things happening here. We're going to really see the pattern on the next one if you don't see it yet. So a sub 4. A sub 4 says if you want to find the fourth term, take the index of 4, plug it into your n, that would be your the subscript of whatever term you want to find is going to find that particular term for you. So take the 4 and plug it into your formula up there for your sequence. That would be -1 to the 4 minus 1. Four over 2 times 4 minus 1. Well, what's going to happen? This exponent is now odd. Notice how it was acting like even, then odd, then even, then odd, then even, then odd, then even, then odd. That's what you get with n minus 1. You're going to get an even or an odd number. It's just going to be off from whatever index you're putting in. So if you're plugging in an even, it'll give you an odd. If you plug in an odd, it'll give you an even. How could I make it match up? So if I plug in an even, it gives me an even. Plug in an odd, it gives me an odd. I just wouldn't have the -1. So whenever you see -1 to the n or -1 to the n minus 1, it's going to give you a sign alternation for every term, every time. In this case, we have an even number. Even numbers -1 is odd. -1 to the third power, or an odd in general, is going to give us -1. Our fraction is, numerator is 4, denominator is, 8 minus 1 is 7. I really want you to think about the pattern right now. We started with +1 over 1, then we got -2/3, +3/5, -4/7. Think about what's happening. What's the next one going to be? Think about the pattern. It's very important for you to find the patterns. The next one should be positive or negative. Should be positive. The next numerator should be, let's see, 1, 2, 3, 4. The next numerator should be 5. The next denominator should be 1, 3, 5, 7. The next denominator should be 9. You can do that with the patterns. You can find out each little piece. Am I dealing with a positive or negative? In this case, I should be alternating signs, get positive. What's my numerator doing? 1, 2, 3, 4. It should be 5. What's my denominator doing? In general, 2n minus 1 will always give you odd numbers. It's listing out the odd numbers. 1, 3, 5, 7, and 9, because the denominator here would be 1. Remember that? The denominator was 1. The numerator is just listing out, oh, wait a minute, if that's based on n, and n is always just the natural numbers, it's giving my counting numbers for every term. It should give me that fifth term. And if we look at it, this is 5 minus 1, that's 4. Negative 1 to the 4th power is positive 1. Your fraction is 5 over 9. And that's what we expected to happen. So if we want to list out our first 5 terms for our sequence, the first 5 terms are really positive 1 over 1, but we've simplified that, haven't we? We've got 1. Then negative 2/3, positive 3/5. Negative 4/7. And positive 5/9. So if we're asked to just find the first 5 terms, we've done it. Hopefully you've noticed what's going on here. The alternation of signs, the numerator matching up with whatever your index is, 1, 2, 3, 4, 5. Denominator is matching up with the odd, every odd number. So we're basically skipping evens. That's what 2n minus 1 does. So we're having 1, 3, 5, 7, 9, the sequential odd numbers here. If you want to show the sequence in general, just to show the pattern, you'd have this, you just put a dot, 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 and then do that negative 1 n to the n minus 1 n over 2n minus 1. Typically, though, we're just asked to find a certain number of terms. If you want to show that, that's okay. What if you had to find the 10th term? Well, then we plug in 10, and we do whatever the math says. In our case, we have 10 minus 1 is 9. Negative 1 to the 9th is negative 1. Then you'd have 10 over 19. So that would be 10 over 2 times 10 minus 1. And you get whatever term you actually need to define. I hope this makes sense. I hope you've seen what a sequence is. It's not super complicated, but it is important. Very important for a lot of math that we do, especially later on when you get to like calculus 2-ish. So it's just this list of numbers. It's based on whatever your index is, and it needs to give you a formula for that. Right now, what we're going to do is we're going to go backwards. I'm going to give you the list of numbers. I'm going to show you a couple techniques on how to go backwards and find your sequence from it. I'm not going to give you incredibly hard examples to do. I'll make them understandable to you so you have a process for doing it. I'll see you in a little bit. Now that you understand what a sequence is really about, let's try to go ahead and create our own formulas from some sequences given. Very important piece of understanding is how to find a pattern and represent it so that you don't have to list out the sequence to find like the 100th term. You probably don't want to do that here. So if that's your first term and I said, find the 100th, 1, 2, 3, here's the 4th, and you go, I don't want to find like 96 more terms to just find the 100th term. That's crazy. I don't want to do that. I want to spend the time to find the pattern, relate the pattern to the index, and in doing so, you find the general term. If I can find the general term, I can plug in any number and then find the 100th term very, very easily. That's the idea. So I'm going to give you a way to do it. I'm not saying that with these examples is exactly how everything is going to work. What I'm saying is this idea will yield for you this formula for your sequence. It's the best way I found out how to do it. So some of these can be quite tricky, but in general, here's the idea on going through and taking a pattern, this list of numbers, and figuring out your general term from it. So number one thing we want to do, take your terms and write them down. So if I give you 4 terms, write down a sub 1 is this term, your first term, and second term, third term, fourth term, however many you have. Then make them all look the same, so the same form. If most of them are fractions, make them all fractions. If we have a sign, show that as -1 out front or 1 out front. If we have powers, relate them all to the same type of base, if you can. So somehow find out a form that all of these take. After that, make the jump to n. We're about to do that right now. So number one, the first thing I'm doing, I'm not really overthinking it. I'm just going to write down all 4 terms. Next, what I'm going to do, I'm going to make them all appear the same form if I can. So for instance, I've noticed that these are fractions and that isn't. I'm going to write that as a fraction. Take the one that's off and write it as whatever the rest of them are. After that, what we're going to do is we're going to try to write them as something that can be represented the same in all of them. Are we doing odd numbers? Is there something like we have a power of something? So I'm looking at my numerator and saying, well, my numerator is 1 in every case. That's really good. So I'm fairly confident that every single term is going to have a 1 on the numerator. And now I'm going to look at my denominator and think, what relates 2 and 4? And now the 1's throwing me off, so I'm going to leave that for a second. What relates 2 and 4 and 8? Could you think about the next term? 2, 4, 8. What are you doing? Well, it appears that I'm multiplying by 2. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is, it's probably 16. Now that's great. I could say I'm multiplying by 2, but maybe I could also think about this as powers of 2. So the reason why is because that doesn't have a 2 in it. So it's really hard to multiply something by 2 and get 1. I don't want to start dealing with fractions like that. So maybe I think of powers of 2. Like this is 2 to the first. Oh, 2 to the first, 2 to the second, 2 to the third. Next will be 2 to the fourth. Now, unfortunately, though, you have to have everything related the same. So if this is 2 to the third, 2 to the second, 2 to the first, what would 1 be? We know about that. We know that if oh wait, how about 2 to the 0? 2 to the 0 would give me 1. So I've listed out my terms doing nothing. I've made them all the same form. They look like fractions. I've tried to relate them somehow to the same something, whatever you're multiplying by, or a common base. I have found a common base, 2 to the third, 2 to the second, 2 to the first, 2 to the 0. And let's double check. Does this still give me 1, 1/2, 1/4, and 1/8? Yes, they're all the same. And now, finally, once I have them all the same form, I somehow relate whatever is changing to whatever my index is. Whatever's changing to whatever my index is. So the 1 is not changing. You know what that means? That means that this is going to show up in our final formula as 1. The 1 doesn't change. 1, 1, 1, 1. This is going to have a 1. The 2 does not change. 2, 2, 2, 2. This is going to have a 2. The exponent of the denominator is changing. 0, 1, 2, and 3. I need to relate that to my index. So I'm going to try to come up with some sort of an expression based on n, based on my index that represents this. So how can I do that? Well, let's think about it. How is 3 related to 4, and 2 related to 3, and 1 related to 2, and 0 related to 1? It appears that what I'm doing is I'm taking my index and I'm subtracting 1 from it. It looks like this is taking 4 minus 1, giving me 3, 3 minus 1, giving me 2, 2 minus 1, giving me 1, 1 minus 1, giving me 0. So I'm relating this to whatever my index is, and now we're ready to make the jump. As soon as you have the index listed somewhere in your term, that should be the only thing changing, is the index should be changing. So list those things out. Whatever is changing, 1, 2, 3, 4, 1, 2, 3, 4, call that n. So I know that I have 1, that's not changing, here's a 1. 2, that's not changing, here's a 2. Minus 1, that's not even changing. I'm going to have a minus 1. The 1 matches my 1, my 2 matches my 2, this exponent, that part of the exponent is matching my index, called an n, and this represents the sequence that we have. So if I wanted to find, check it if you want to. If I wanted to see term number 1, I should be plugging in 1 and getting out 1. So if I plug in 1, 1 minus 1 is 0, 2 of the zeros, 1, 1 over 1 is 1. Let's check term 4. Plug in 4. 4 minus 1 is 3, 2 to the third is 8, 1 over 8 is 1/8. So it does work, and I hope that sequence of steps makes sense to you. Write out your terms, don't change them. Make them the same form. You should be able to. Find out some relationship amongst the terms. Are you multiplying? Are you adding? Are you adding the same number? Are you taking a power like we are here? And then try to relate it to your n. Do you necessarily have to show this step? No, not really. You could probably get there from here and go, hey, you know what? That's 1 minus 1. That's 2 minus 1. That's 3 minus 1. That's 4 minus 1. That's n minus 1. You can totally do that. I'm giving you as clear as I can make it, my thought process going through this. Now, could you find the 50th term, the 12th term, the 100th term, that whatever you want? Yeah, you could. If you wanted to find the 10th term, let's say, because I really don't want to plug in a big number, a sub 10, you would just plug in 10. That would be 1 over 2 to the 9th. Because 10 minus 1 is 9. That's a whole lot better than writing out all these terms until you get there. And you could evaluate that 1 over 2 to the 9th, figure out what 2 to the 9th is, and then you'd have a nice fraction. So I hope that makes sense. I hope a lot of times, students really struggle with this in Calculus 2. I teach this in Calculus 2. And sometimes students go, I don't know what that means. I'm trying to develop for you a thought process for how to take a sequence, which is a pattern, and write it as something meaningful that you can find other terms with without having to complete the entire sequence. It's a very valuable thing to be able to do. All right, let's move on to the last one. We're going to do the same thing. We're going to talk about this. We're going to see what the patterns are. We're going to relate it to our index, and then we'll have a general term. So b sub n is 2, then negative 4, then 6, then negative 8, then 10, then what would the next term be? What would the one after that be? Can you see that the next term should be, well, think about it, should it be positive or negative? Start evaluating this sequence. I see positive, negative, positive, negative, positive. Next one should be negative. I see 2, 4, 6, 8, 10. The next one should be 12. These are alternating even numbers. What we're going to do is we're going to try to create a sequence for that, a general term for our sequence, but it starts with listing these out. So take them and write them down for every term. I've given you 5 terms. Let's write down 5 terms. Now, let's all make them look the same. So what do you mean look the same? Well, let's start by saying these are all even numbers, but I'm seeing that they have a negative in front. When you see that, try to do this. Try to make it so that you can relate it to 1, where you either are multiplying by 1 or negative 1, 1 or negative 1, 1 or negative 1. So every negative number can be represented as negative 1 times that value. Now that looks really funny, but that would look funny if we were just saying, oh, well, certain numbers I want are multiplied by negative 1 because I feel like it. So with the 6 and the 10 and the 2, consider that it's still being multiplied by 1, but somehow not giving you a negative. That starts to look the same. Are you seeing what we're trying to do? We're trying to get every term to look the same form. So here I said 2, negative 4. Well, I really want them to have some feature that's the same. This is negative 1, this is positive 1, this is positive 1, negative 1, positive 1. Next one would be negative 1, then positive 1, then negative 1, then positive 1. It's giving us an alternation. Now let's try to define what that 2, 4, 6, 8, and 10 is, and then we'll finalize what's happening with the 1 and negative 1. Now I've prefaced this. I've shown you an alternating sequence where you're probably going to have negative 1 to some power. That's exactly what we're going to have. We just need to tie it into the end somehow. So let's take a look at our 2, 4, 6, 8, and 10. Well, they're all even, which means that I can relate this as 2 times something. In other words, 2, 4, 6, 8, and 10 are all something multiplied by 2. So let's write that. At this point, when I took this class or something similar to it or studied this for the first time, I thought, how in the world is this person figuring this out? I'll never be able to figure that out. It does come with practice, I will tell you that. But it's also this thought process of getting them to look all the same will really guide your thoughts. Like, how can you make these all look the same? I know 2, 4, 6, 8, and 10. Well, it looks like they're all something multiplied by 2. I just write the 2. This would be 2 times 1, 2, 3, 4, 5. That would give us 10. That would give us -8, 6, -4, and 2. It's the same sequence, but now I have it written differently so I can evaluate how it's related to my index. Now we start looking for the pieces that are changing and the pieces that aren't changing. So what's not changing here? What's not changing is going to show up as a constant in your formula. What's not changing is 2, 2, 2, 2, and 2. That's not changing. Another thing that's sort of changing, but not really, is you're going to have a -1 here. If you're -1, not always have -1s. That's true. That's because it will be raised to an exponent that is changing. Whenever you see this positive, negative, or negative, positive, or 1, -1, 1, -1, or -1, 1, you're going to have a -1 in there raised to some exponent. That's what alternation does. Now, it is up to us to figure out what that exponent is. We're going to do that in a minute. But these are two things that aren't changing. The 2, and there will be a -1 on every one of those terms. What is changing needs to get related to the n, the index. So we start doing that. 1, 2, whoa, that's cool. 1 matches with 1, 2 matches with 2, 3 matches with 3, 4, and 5, and n. Notice how that is exactly what we're doing here. This is 5 matches with 5, so n matches with n. That's what we're doing. We're relating the things that are changing to the n's that are changing, our index. And in this case, it's just whatever n shows up. So 1 should have a 1 here, and 2 should have a 2 here, and 3 should have a 3 here, and 5 should have a 5 here, and 10 should have a 10 there. And that's exactly what is happening. Now, we got to do our sign. So the way to deal with this is to either take this to the n or the n minus 1 power, depending on whether the first term is positive or negative. So if your first term is positive, you need a 0 to get that. If your first term is negative, you need a 1 to get that. Since we start with our first term and we have a positive, you're going to have to take that 1 and subtract 1 from it. And you know what? Right now, probably the best way to deal with this, just trial and error until you really understand what's going on. Try to plug in 1 and see if it gives you a positive 1. If it doesn't, then change this and just make it an n. So let me show you. Let's pretend I did that. If I tried to plug in 1 for my first term, I would get -1 to the first. It would give me -1, and I'd go, oops, that's not right. So what do I do with that? Subtract 1, and it'll work. Now plug in 1. 1 minus 1 is 0. -1 to the 0 power is 1. 1 times 2, that's 2 times 1, would give us 2. Oh, that works. Try the rest of them. Let's plug in 2. 2 minus 1 is 1. -1 to the first is -1. Got it. And then remember, we're plugging in 2 here. 2 times 2 is 4. Try the third term. Plug in 3. So if I plug in 3, 3 minus 1 is 2. -1 to the second power is positive. Great. And then 2 times 3 is 6. It works. It can work for all of them. This is much nicer than writing out the first 50 terms if you need to find b sub 50 or the 50th term. For the 50th term, it wouldn't actually be that bad. For the 50th term, we'd have -1 still. That doesn't change. Only the n's change. That's why we write this in the identify the only things that are changing. Because if only the n's change, you just need to see the things that are changing and call them n somehow. That's all we're doing. It just takes a lot of thought to do it. So -1 doesn't change. 50 minus 1, while that seems like a large number, it's really just about being even or odd. So 50 minus 1 is 49. -1 to the 49th power, -1 to an odd power, is negative. 2 doesn't change. 2 is where we're getting the evenness from. This is how you represent even numbers, is 2n, for whatever n is a positive whole number. So 2n would give you all even numbers. The first whatever even numbers you want, 2, 4, 6, 8, and 10 are the first 5 even numbers. And then 2 times 50 would give you 100. It should make sense to you that the 50th even number is 100. There's 100 digits in a row, right, if you count them. The first 50 odd numbers are 1 through 99, yeah, you don't count that 0. And the first 50 even numbers end with 100. So hopefully that makes sense to you. We just have negative 100 because we have that alternation. This is how you, and this looks a little awkward. I really should have a little more space for that exponent, even though that's just on the negative 1. Typically, your alternation is written first, though, so that you can immediately identify and go, oh, yeah, that's alternating signs. And it's going to start with a positive. Then the next would be a negative, positive, negative, positive, negative, if we start with n equals 1. Okay, this is a really common example to get on like a test or something like that. So just check out how it really works. Make sure that when you're trying to go and find a sequence from a list of numbers that you write them all out, you try to make them in the same form. I'm just going to give you this extra one because I think you should try it on your own. I really do. Try to follow that. Try to write them all out, all 4 of these terms. Try to make them the same form. Identify what that negative, positive, negative, positive, negative, positive, negative, positive doing. The next term should be negative. It's alternating. Try to identify that they're all fractions. Write them in the same type of a fraction. What do you mean the same type of fraction? See if there's a root fraction here that's repeating itself, maybe by a power. Sometimes you can multiply the same number. Sometimes you have to find a power. So for here, we're going to take and say, this is negative 1 times 2/3. This is positive 1 times 2/3. And negative 1, 4/9. I'm doing the math in my head again. 4/9. And negative 1 times 8/27. And positive 1 times 16/81. Now, these fractions don't look the same, but see if you can make them the same. Think about 2/3. Can you relate 4/9 to 2/3, 8/27 to 2/3, 16/81 to 2/3, or all of them to some other fraction like we did here? Can we relate all these to 2 times some number? So for us, keep your negative 1, keep your 2/3, keep your 1, but let's think about 4/9. Can you write 4/9 as some root fraction? Well, this would be 2/3 to the second power. 2 to the second over 3 to the second. Now, you could write it that way too. 2 to the second over 3 to the second. This is 2 to the first over 3 to the first. And 2 to the third over 3 to the third. And 2 to the fourth over 3 to the fourth. Can you make it even simpler? Can you say, well, wait a minute, because the numerator and denominator both raised at the same power, can we really factor that power out over division and have 2/3 to the first, 2/3 to the second, 2/3 to the third, 2/3 to the fourth? Now we're about ready to start writing down our general term or the formula for our sequence. Identify the things that are not changing. The things that aren't changing are, you will have a 2/3. You will have a negative 1. And you will have some exponents. Nicely, our exponent 1, 2, 3, and 4 matches our index. So if that matches our index here will represent that exponent. So 4, 4, n, n. Just like every other index matched its power. As far as our negative 1 goes, we need to get that alternation correct. So we start with a negative number. So try something. Try n. Is negative 1 to the first power going to give us the negative that we want? Yes, this matches. I think guessing and check, until you understand it, guessing and checking is pretty okay to use for your alternation. So because we start with a negative, we need to start with an odd power. Our first term is odd, so let's start with the first power, or the second power for second term, third power for third term, fourth power for fourth term, nth power for the nth term is how we really determine that. This is the general term for whatever that sequence represents. One other thing, keep in mind that for odds, it would look up very similar to that, but you'd have to start subtracting 1. Maybe I'll go ahead and do that one too. Okay, my personal opinion is that the odds can be quite difficult because while they're easy to define recursively, you understand what's going on as you look at your pattern and you can base it on your previous term. That's what recursive means. For instance, I can look at this and go 1, 3, 5, 7, 9. The next one's gonna be 11, 13, 15. They're odd numbers. I can see that. I can see how to find it. I can see that I'm taking the previous number and adding 2. Previous number adding 2. Previous number adding 2. Previous term adding 2. That's a recursive formula and be pretty easy to find. You can say that a sub n would be the previous term plus 2. That would actually do it. If I want to find the fifth term, oh man, this is pretty advanced actually for recursive formulas. If I want to find the fifth term, I'd look at the fourth term and add 2. If I want to find the fourth term, I'd look at the third term and add 2. So if I wanted to find a sub 4, I'd look at 4 minus 1 is 3, and I would add 2. So if I want to find the fourth term, I'd look at the third term and add 2. And now ignore the A's versus B's. I'm just giving an example here. But this would be look at your previous term and add 2. Sixth term would be look at the fifth term and add 2. You get 11. Do you see how recursion works? Do you see how it's looking at your previous term and doing something to it to find your next term? It's almost like induction when we get there. But it's saying you need to know your previous term in order to find it. Sometimes you need to know your previous finite number of terms to find it. So if I wanted to find the 100th term, this would not do it because I need to know the 99th. If I want to find the 99th term, I need to know the 98th. So while we can define things by the pattern and say, yes, there is a pattern. The pattern is look at your previous term and add 2 to it. Look at your previous term and add 2. Look at your previous term and add 2. Look at your previous term and add 2. That's exactly what it says. It's not beneficial to find the nth term or general term. This is not it. So it's quite difficult, really, because when we take a look at this and go, man, I don't know, how am I supposed to relate all these to the same thing? You have to think outside the box here. We try to relate to n. 1 equals n, okay, but this doesn't equal to n. 3 doesn't equal 2, and 5 doesn't equal 3, and 7 doesn't equal 4. It looks like it's 1 more, then 2 more, then 3 more, then it's predictable, but it's not really matching up perfectly to the thing that's changing. So instead, let's try to relate them to something else. Let's try to relate them to something that's not changing. For instance, I noticed that, this is 1 and 3 and 5 and 7 and 9. I can think of it as this is 1 less than 2, 1 less than 4, 1 less than 6, 1 less than 8. Well, and in doing so, I have something that's not changing. I have this minus 1. I have a minus 1 that's not changing. Okay, now that took some thinking outside the box though, didn't it? Because it's really hard to relate that if you're not used to it, but now you've seen it. Doesn't mean you're going to be perfect at it right now, but at least you're kind of exploring that thought. Now, how about 2, 4, 6, 8, and 10? Can I relate those little pieces to something that's not changing? Well, it appears that 2, 4, 6, 8, and 10 are all multiples of 2 again. That's 2 times 1 minus 1, and 2 times 2 minus 1, and 2 times 3 minus 1, and 2 times 4 minus 1, and 2 times 5 minus 1. We have another thing that's not changing. We have a 2. Every one of those is true. It's going to give you 9 and 7 and 5 and 3 and 1. And we've identified the pieces that aren't changing. Do you see the point? The point is you need to identify the pieces of your sequence that are not changing and write them down. Then relate the thing that is changing. And it has to relate the same way in every term to your n. That's why this screws us up so much. It's not related the same way to our n every time. We can't just go, oh, this related to n is equal, but this one is you add 1, and this one is you add 2. That doesn't work. That doesn't work at all for sequences. It must, whatever you have done here, The changing piece must relate to your n the same way for all of them, which is why this takes so much work. You go, well, I don't know. This doesn't look like it relates really well. It's related to something else. This is 2 minus 1, 4 minus 1, 6 minus 1, 8 minus 1, 10 minus 1. Oh, I'm subtracting 1 every time. Great, I have a minus 1. Let's look at our 2, 4, 6, 8, 10. Do those relate to something? Well, I have 2 times some number for every one of those. So I've related that. That's why we got a 2. Now it's pretty nice because we have 1, 2, 3, 4, and 5 for n equals 1, 2, 3, 4, and 5. It appears that our index is here, 2 and 2, 3 and 3, 4 and 4, 5 and 5. The piece that is changing is just our index. It's n. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, n, n. Relate the part that's changing to your index, and we've done that. It's just our n, whatever our index is, appearing. This is actually the sequence. This is the general term, and that is how odd numbers are defined in like number theory and things like that. Even is 2n. Odd is 2n, and you just subtract 1. So you'd get 2, 4, 6, 8, 10, and subtract 1 from it, you get 1, 3, 5, 7, 9. It's actually much more difficult to define, right? Because you have to base them on even numbers and say, oh, I'm subtracting 1 from it, which is where this comes from. Here's all your even numbers, and to get the odds, you subtract 1. That's why I wanted to show that one to you. I hope it's made sense. You can do this recursively, like I said. You can say, my next term will be based on my previous one. My next term, my 6th term, would be based on my 5th term plus 2. And you can do it that way. This is a recursive type of formula. It says based on previous terms. This is not. This is a straight up formula for the sequence. This one will allow you to find the 100th term if you want to. The 100th term would be 2 times 100. That would be 200 minus 1 is 199. 199 is the 100th odd number. This will not let you do that. You'd have to know the 99th term to be able to figure out that 100th term. And it does work though. So like if I just told you b sub 100 is 199, the term right before that would be 197. So the odd numbers would be 197 and 199. The 99th term would have to be 197, and then we'd get 189. Those are sequential odd numbers. So check it out. If I wanted to find the 100th term this way, I would have b sub 100 should equal b sub 99, the previous term. Notice how 100 minus 1 is 99. 100 minus 1 is 99 plus 2. Well, do you know the 99th term? Yeah, because I gave it to you. The 99th term is 197 plus 2. So recursive formulas have to look at the previous term or terms and do something to get your current term. So b sub 100 says, look at your previous term and add 2. Look at your previous term, 187, and add 2. Oh, I should get 199. That is my 100th term. But it requires a lot more information to do that. It requires previous terms information. All right, I've really gone way further than I intended to on this video. I just got kind of excited about the sequences. So hopefully you understand a lot about sequences now. You understand that they're a list of numbers, they're not added. They're just a list of numbers. You typically find the first 5 or so by a formula. The hard part is going backwards, getting a list and then creating a formula for it. I have given you some very good ideas on how to do that, how to relate it in the same form, how to relate it to something that's not changing, how to write those not changing pieces as part of your general term, and then relate the piece that is changing somehow, and it does not have to be easy, to your index, and that will be your n in your general term. So I hope I've made that make sense to you where this stuff comes from. It takes a lot of practice, but in the next video, we're going to talk about series, taking your sequences and adding them up. So I'll see you for that.